Hello, everyone. This lecture is going to combine two of the themes that we have previously discussed in this lecture series, the theme of philosophical naturalism and the role that the social structure of science plays in the success of science. Quick recap. Philosophical naturalism in this context is the idea that there is no hard and fast distinction between science and philosophy, that they're both engaged in the same principal enterprise of trying to understand the natural world. The job of philosophy is not some abstract metaphysics and try to understand the fundamental structure of reality that transcends the physical, as it might have for Plato, for example, but also nor is it just to be the handmaiden of science the way the logical positivists thought, where sort of the job is simply to get conceptual clarity and linguistic rigor down so we can talk more productively about science. Rather, there isn't a hard and fast distinction. They are doing the same basic thing. They're just doing it with slightly different methodologies. Now, the traditional empiricists, both the old school folks like John Locke and David Hume, as well as the logical positivists, didn't really pay much attention to the role of the social structure of science. They were concerned more just with the role of experience and with the logical structure of science. They weren't terribly interested or concerned, or even to a certain extent even terribly aware of the role that the social organization of people working in cooperative and competitive structures in science helped to produce the thing that we call science. One of the big turning points in this conversation, of course, was the work of Thomas Kuhn, namely his book, The Structure of Scientific Revolutions, which was then built on by sociologists of science in the decades after that was published, that tried to sort of show that empiricism, as traditionally construed and as well as construed by the logical positivists, was fundamentally incapable of fully understanding what science was about because it was blind to this social dimension. Now, again, the principal idea of what naturalism is going for is to try to sort of learn from this mistake and recognize that philosophical reflection should be able to sort of transgress boundaries. It should be able to not simply concern itself with matters of raw experience, but should also be able to draw from lessons within other fields such as mathematics and sociology and psychology, and of course the particular scientific disciplines that were contributing to science more broadly here. It's around this time, we're talking about maybe the mid-1980s to the early 1990s, that a lot of philosophers of science steered away from being just sort of generic catch-all philosophers of science and started focusing more on particular disciplines like the philosophy of chemistry or the philosophy of biology or the philosophy of physics. And a clear example of this is the work by philosopher David Hull. Hull wrote a 600-some-odd page book called Science as a Process, in which he tried to sort of extract lessons from evolutionary biology and extrapolate from them to the development of science as a whole, historically and contemporaneously. He used sort of a Darwinian framework of thinking about competition for ideas and resources as a way of understanding how it is that certain scientific theories and ideas flourished and other ones withered away. Hull's work is pretty complicated, pretty sophisticated. Again, he's trained as a philosopher, but as I said, he is part of this relatively new school that is getting so saturated in the nitty-gritty details of particular sciences, in Hull's case biology, that his work really starts to bleed pretty in a way that's hard to draw a hard and fast line from a lot of work of theorists within biology. He didn't do field work in the way that, say, Charles Darwin himself did, or a lot of biologists do today. But Hull spent a lot of time actually hanging out with real biologists, talking to them, learning about their methods, having conversations with them about their theories. And so he's kind of blurring the line between philosopher, biologist, and sociologist. He's using sort of sociological methods, interviewing the actual practitioners. But what he's interviewing them about is their biological training and their biological ideas, and he's using his philosophical toolkit and training to do that. So this is, again, sort of the naturalistic approach here. It's sort of breaking down these barriers and trying to sort of use them all holistically or collectively as a way of better understanding our subject matter. Hull starts with a set of some fairly common sense assumptions here. He starts with the assumption that scientists are first and foremost curious about the world. They go into science, either that, do undergrad or grad programs, or they go off to work in labs. They do this precisely because they first and foremost want to understand the world better. Obviously, not every curious person goes into science, but this is a important aspect of science and scientists that draws them into the field in the first place. Obviously, it's possible for someone to get into science just because they want to make money or something like that, but that's an uncommon sort of thing in Hull's opinion. Hull thinks that most scientists do it first and foremost as a way to pursue their curiosity. So Hull borrows from the work of Robert Merton, a scholar who we've talked about before. Merton, remember, is a sociologist, one of the pioneering sociologists of science, and Merton's idea was that we should understand science as both a cooperative and a competitive enterprise. Neither of these two elements is more fundamental than the other. They both have to be in the mix, and sometimes one may be a little more active, a little more central to a particular disposition, a particular question or theory or laboratory or what have you. But broadly speaking, across science writ large, there's always elements of cooperation and always elements of competition. It's the interaction between these two forces, between the competition and the cooperative nature of scientists, that actually drives science forward. Now, according to Merton, the principal currency that science as a social structure uses to reward individual scientists is the idea of recognition. You give them credit. Again, the most obvious example of this would be a Nobel Prize, but there's lots of other ways in which science doles out recognition too. So, according to Merton, the primary desideratum of a scientist, the thing that a scientist wants more than anything else, is the esteem and the recognition of their peers. When the rest of the scientific community looks up to you and considers you to have made important contributions, that's when you've made it. That's when when a scientist truly feels like they've done their job well. Now, Hull expands on this notion. He thinks it's basically right, but he wants to say there's a particular form of recognition that Merton didn't quite key in on, and that's the idea of use. Scientists feel most recognized when other people use their ideas, when they build off them, when they replicate their experiments, when they expand them into new areas, when they show elements or aspects of it that the scientists themselves didn't recognize when they first did the original work in the area. When a scientist is cited, when a scientist has their ideas applied in this way, that's when scientists really sort of feel like they are getting the recognition that they deserve. Scientists want other scientists to use their work. They want their work to be a part of the ongoing process of science. It's not good enough that people just say, oh yeah, this is good work, and then they leave it and they never come back to it again. No matter how many compliments you get, no matter how many awards you get even, it doesn't really matter unless people continue to build on your work. And so this just brings us back to a point that we made earlier, that science is something that we have to do collectively. No one person can do science all on their own. They need to build on the ideas of other people, and they need to use the ideas of other people, and they want, in turn, other people to use and build on their ideas. Scientists need to cooperate and to trust one another. And so that leads us into the next sort of main section here on the role of trust in science. Now, the sort of traditional picture of science, the one that's sort of championed by classical empiricists, for example, basically sort of denies a role for trust. The basic thought here is that as long as science is replicable, other people can check the work. So there's no need for trust on this sort of traditional way of thinking. You don't need to trust, you just need to verify, if I can sort of steal that phrase a little bit from Ronald Reagan. And again, there's obviously some truth to this. Work that isn't replicable isn't considered to be legitimate science. It isn't considered to be something that either makes its way into the history books or is going to be used by other scientists. No matter how impressive the initial experiment is, if other scientists can't replicate it, then it's dead in the water. Probably the classic example of this is the work of Martin Fleischmann and Stanley Pons, who in the late 1980s claimed to have discovered cold fusion. They were a pair of electrochemists, and cold fusion, really quickly if you're not familiar with it, is trying to take the process that generates energy in the sun, which is hot fusion, obviously, and run it at room temperature. So, if you've ever seen Back to the Future, Mr. Fusion is presumably a version of cold fusion, right? You can take energy from any sort of matter and fuse the atoms together to release energy. And if this worked, this would have been absolutely revolutionary. If cold fusion actually were possible, it would solve so many energy problems. It would transform the economy. So in 1988, 89, I think it was, somewhere there about, when Fleischmann and Pons claimed to the world that they had made cold fusion happen, it caused a firestorm. Scientists and the media were really interested. They wanted to see what was happening. And this got a lot of coverage and a lot of attention. And unfortunately, no one was able to replicate their work. I'm not savvy enough to know exactly what went wrong. I do know that Fleischmann and Pons never retracted their work. They never admitted to making a mistake. I don't think there was ever any accusations of out and out dishonesty. I think it's just they made some sort of simple mistake, presumably. And physics and chemistry are challenging subjects. So in spite of all that initial excitement, when other people couldn't replicate the work, it was discarded and not built on. So that's a good example of how replication and replicability can check against mistakes, but it also checks against fraud. Again, I don't think Fleischmann and Pons were out and out trying to defraud the scientific community, but lots of other people have in various capacities, because people sometimes want to cheat. They want to get that recognition, they want to get that use, but they don't want to put in the honest work to have it done. So this criteria of replicability, which is, again, something that it requires sort of a social structure to do, is essential for science working properly. But there's obvious limitations to this idea of replicability. No individual scientist can check every single background experiment. You might be able to check some, obviously maybe the core ones that are central to the ideas that you're building on, but there's always going to be other ideas, other theories, other instruments that you as an individual scientist simply don't have the time or even the ability or the capacity to calibrate or check or to try to replicate their other work. So at some level, the individual scientist just has to trust that other people have done their job. They have to trust that the scientific community, someone in the scientific community would have caught this at some point if it wasn't replicable, if it hadn't been done before. Now, obviously, to a certain extent, you can do a literature search. You can check and see if other people have done it. But even then, you have to trust that the people who are claiming to replicate it knew what they were doing. It's not possible to carry all this weight by yourself. You have to distribute some of this epistemic labor to the scientific community writ large. Now, most checking occurs when people are already relying on that work to develop other research ideas. If someone else is using your ideas and there's a problem with your ideas, sooner or later someone's going to trip over the problems in your ideas because their ideas aren't going to pan out. Their theories, their experiments aren't going to work. So they're going to have to go back and double check and figure out what the problem is. And if they find the problem in your work, then that's a problem. And that's a good incentive to make sure that before you publish that you do your due diligence and that you put your epistemic labor into your work so that other people, when they build on it, will be able to rely on it successfully. Now, sometimes, of course, an idea displaces old ideas, and of course, scientists can get territorial, right? If you were at the top of the hill for a decade in a particular field, and some young upstart comes along and publishes a new paper challenging your ideas, you're going to have a powerful incentive to double check their work and make sure they did it right. Because if they did do it right and they displace you, you're losing your standing. People aren't going to use your work as much; they're going to use the new stuff. So there is this sort of competitive incentive for people to check each other's work when they're challenging one another not for priority, excuse me, but when they're challenging one another for who has sort of the better theory or the better take on this particular discipline or area. Now, Hull also offers a sort of a particular vision of the social structure of science, which boils down to sort of two basic elements that are harmonized with some of the things that we've been exploring so far in this lecture series. The first is this idea that I've already been talking about, this idea of the individual desire for use. Each individual scientist wants other scientists to use their ideas, to build off them, to expand on them. And then the collective group replication of work. The scientific community as a whole will replicate these experiments and build on these ideas and check them as they build on them. And it's this sort of 1-2 component here of the individual wanting other people to use their work and then the group replicating the work of the various individuals that manages to strike a nice balance. It channels the selfish motives of individual scientists to produce good work that benefits the collective scientific community and, of course, presumably broadly humanity as a whole on top of that. In a lot of ways, this is similar to Adam Smith's notion of the invisible hand in economics. If you're familiar with that notion, I won't delve into it here, but it's a pretty popular idea that you may have heard of before. And it's kind of this idea that social organization, whether it be scientific or capitalistic, can bring about improvements in our situation simply by organizing the individual motives of people into a collective social structure that allows them to build on one another. Now, this in some ways echoes back to the work of Karl Popper that we talked about before. Popper, remember, stressed this dialogue between creativity and criticism, this idea of conjecture, which is the creative aspect of science, and then refutation, which is the critical aspect of science. Science is conjecture and refutation was sort of one of his core ideas, that idea of falsifiability. And this was a popular idea, and Hull's going to put an interesting spin on this. Hull says that there's actually a division of labor here as well. The individual creativity comes from the individual scientists. When they come up with a new idea, when they put a new idea out, when they publish a paper, that's the scientist being creative. But unlike Popper, whereas Popper says the individual scientist has to criticize their own ideas to avoid the dogmatic attitude, Hull doesn't think that the individual scientist needs to worry about criticizing their own ideas, because that's where the rest of the scientific community comes in. The scientific community will criticize the ideas that you put out there quite vociferously. If you make a mistake, they will find it. So you don't have to worry too much about double-checking yourself. I mean, obviously, you should double-check yourself some. You don't want to make a silly mistake or an obvious mistake. But Hull seems to think that the best way to move forward is for scientists to be fairly liberal in the ideas that they put out there, and then fairly conservative and critical in terms of what ideas they accept from the rest of the scientific community. And so you have that sort of that balance between creativity and criticism, that dialogue that Popper talked about. But instead of being inhabited in a single individual scientist, it's set up in the relationship between individual scientists and the scientific community at large. Okay, well, this brings us to sort of a related psychological question now. Why should scientists care about use? Why is that something that seems so rewarding to them? Why is it something that matters? You can't pay your rent with recognition, like the saying goes, right? Information wants to be free, but rent wants to be paid, right? Why shouldn't scientists care more about monetary compensation the way a lot of people seem to do? There's plenty of scientists out there who have made incredible contributions to scientific understanding and are fairly poor, fairly modest in their means. So given that science can be leveraged to make money, and again, some scientists do that, why is it that money doesn't seem to be, according to Hull at least, one of the principal or the primary motivations for most scientists? Why is it that recognition, why is it that use matters so much? Related question to this, why isn't this social structure more widespread? I mean, there's lots of people in the world who aren't scientists, but who nonetheless are curious about things, who want to understand things, and they want recognition. They want esteem. They want people to look up to them and admire them. You can find people like this in the arts, for example, who have some of these similar psychological traits. But while there might be something like this social structure in the fine arts or in ballet, dance, painting, and so forth, it seems distinct. The scientific structure that Hull's talking about here doesn't seem to show up in those other fields. So there's sort of an element missing here. What is it in particular that makes this scientific conception of wanting their ideas to be used in this way different than other people? Now, according to Hull here, this desire for use seems to be a byproduct of scientific and academic training. When you are being taught how to do science, you're also being taught what to value in science as a social discipline. You see your professors or the heads of the labs in which you work striving for publications in top-tier journals and have other scientists replicate their ideas and to build off their ideas. And you sort of emulate these behaviors as you see them. The people that you look up to, your professors, your graduate advisors, you see what they do and you just internalize those values. And if you don't do that, if you don't internalize those values, then you're probably not going to complete your scientific training. It's going to be evident to the rest of the people in your graduate program or in your lab or whatever that you're not like them, and you guys won't get along very well. You probably won't be able to work very well. They will be able to see that you're not in it for the same reasons that they're in it for, and that will create a certain kind of antipathy and a certain kind of disconnect, and you probably won't be able to make it all the way through takes you several decades of training to become a full-fledged scientist. And you can trace this idea all the way back to some of the early scientific societies, most notably the Royal Society of London, who I've mentioned before, and who I'm going to mention again a little later in this lecture. There's very clearly an effort in groups like that to cultivate this attitude, to cultivate the idea that you shouldn't be in it for monetary gain. You should be in it for the idea of making a contribution, and that contribution is only measured and weighed if other scientists deem your contributions worthy. So, we're talking about use then. What is it exactly that is being used? Is there a way we can talk academically about ideas that are used? And there is, actually. And it's a notion that comes from the biologist Richard Dawkins. It's the notion of memes. Now, if you are of the internet, as I suspect many of you are, because you're probably watching this lecture on the internet, when you think of memes, you probably are thinking of things like pop culture pictures with word text on them, or maybe short videos or that sort of thing. And obviously, memes can encompass that, but in its original sense of the word, in which Dawkins coined the phrase, a meme is something more general than that. A meme is any sort of idea that can compete for use, any idea that can compete for people's attention, for people's money, people's laughter, people's recognition and esteem. A religion can be a meme, an economic system can be a meme, a fashion trend can be a meme, and of course a scientific theory can be a meme. So within the scientific community, there's only so much bandwidth, so much attention span, so much stuff that people can try to work on or try to build on. So there's going to be inherent competition. You're putting your ideas out there as a scientist, and other scientists are putting their ideas out there, and the attention span and the esteem and the recognition of other scientists is going to be limited amongst those. Not everyone can get people replicating their work or building off of their work. So you get a sort of inherent competition. And these ideas, these memes, that are the ones that are picked up and that are used and built on, those are the ones that survive. And the ones that are not picked up and built on, even if they get published in reputable journals, if other scientists don't build off them in some way, reference them and use them, then they're going to die off. So Dawkins, as a biologist, coined the idea of a meme to be a parallel to the idea of a gene in biology, whereas a gene is sort of a carrier of genetic information and it codes for traits, phenotypic traits in organisms. A meme is something that codes for information in an intellectual or a cultural community. And so just like genes can compete for survival to propagate themselves, memes can compete for survival to propagate themselves. So this sort of mimetic theory, right, this is a way of trying to understand why it is that some ideas survive and stick around for a very long time, but others die out right away. I mean, again, I mentioned religion before. Think about like the religions like Christianity or Judaism or Islam or Confucianism. These are religions that have been around for over 1,000 years, some of them multiple thousands of years. These are clearly successful ideas. But there's a whole bunch of other religions that were born within the last 100 years, which have since died off. Why is it that some religions succeed and others die off? This study of memetics is a good way of understanding sort of how these social dynamics work, and you can apply this memetic understanding to science itself. And much like in Darwin's way of thinking, it's about the relationship between the gene or the meme and its environment. Some memes are more fit for their social or their intellectual environment than others, and the ones that will be passed around. The fit memes will survive and endure. In the context of science, these are going to be the ones that people find interesting, the papers that are intriguing to people, that seem like they can be built on, that they're doing something novel, but it's also something that's practical. It has fecundity, to use that word, and it's fruitful for other scientists. Other people are going to use it, and that's going to increase its odds of survival. So you have here a process that's basically akin to evolution by natural selection. Memes are born, memes mutate under pressure, they try to replicate each other, they compete with other ideas, with certain economic factors, with social prestige and so forth. So in scientific communities, as in any kind of community where there's competition for intellectual bandwidth or for attention, there's going to be a kind of evolutionary process where the fittest ideas are going to be the ones that survive.